So welcome everybody to this afternoon's webinar from the Nanotechnology Industries Association, looking today at the scale up of manufacture for nanomaterials. I am absolutely delighted to say that we have a packed audience today and had over 250 registrations for people to take part. So I will be reminding people on a regular basis that you need to keep yourselves on mute so that we can keep the audio quality good for absolutely everybody taking part. The webinar is being recorded and will be available on YouTube after the event, and so you'll be able to listen back again at your own leisure. So let's get started and have a quick look at our agenda for this afternoon. The webinar should take no more than an hour, and we will kick off with a short welcome and introduction from me, Claire Scantleberry, from the Nanotech Industries Association, as there is no such thing as a free lunch, so you have to listen to me first. Then we will look at two different aspects of nanomaterials scale up from our member Promethean Particles and also Corning, a large international company. At about 3:40 or 3:45, the public session of this webinar will close, and then we will go into a closed member discussion that will include members and also Corning participants as well. All of those people have already received a notification of what will happen. So at the end of the public webinars, we will ask other people to leave and then move into a closed session. As I've already said lots of times, you are on mute today. I'm very sorry for that because we have so many people taking part in the meeting today. So we're incredibly impressed. But as I also mentioned, this will be recorded so that you can listen back to it later. And we will share the recording with all attendees. So I'm going to give you a very short introduction to NIA to explain what we do and why we host these types of events. So our mission is to support the overall commercialization of nanomaterials to market. And that's a really interesting challenge for a very novel key enabling technology, which is materials at the nanoscale. And that brings a lot of reasons why it needs support beyond standard bulk scale chemicals and other technologies. It's very important for us to help understand what the regulatory pathways to market are and also help shape those regulatory frameworks so that they are robust for industrial use and enable innovation to get to market effectively. We also work really hard to build confidence in nanomaterials. You know, this is a relatively recent technology named as nanomaterials, and it needs as much support as possible to help people become familiar with their use and development and uptake so that it can become a more integral part of products and processes worldwide. And of course, we do a lot of networking within nanomaterials and nanotechnologies because literally the only common factor is the size of the material. It's applied into different sectors with different materials for different applications in different ways. There is something to learn from everybody that you speak to that operates within the nano world. And of course, many of you will be thinking about this within the context of the Green Deal and other environmental sustainability policies being developed, both in Europe and elsewhere. It's very important that nanomaterials can be used with confidence throughout their entire life cycle. And so that involves understanding how that material is going to track through the products and processes to its recycling and disposal. And so that you can work with confidence, both for yourselves and the clients who will buy your materials and use them in their own products. So there's a lot of different reasons that we support the development of nanomaterials, and all of them are very interesting and very diverse. So our core mission is, as I have already said, to support the development of nanomaterials, and we do this in three particular ways. We work very hard around the development of a robust regulatory framework, and with the REACH Annex amendments in January 2020, we've seen a major shift in requirements for reporting and characterization for nanomaterials, and we're working really hard with members now to successfully implement that framework. We do a lot of business and scientific networking and promotion for members because it's incredibly interesting what different companies and researchers do, and so we try to spread this as widely as possible. We also work to build the wider commercial ecosystem in which nanotechnology and nanomaterials operates, because as you will all know in your own line of work, the development of an initial product is not the end of its journey to market. There are many steps that need to get to market successfully, and all of those need to be addressed if nanomaterials are going to be economically successful. This is a tiny snapshot of our members that we have. We have an increasing number of members, over 60 now, I am very pleased to say, and it is getting increasingly difficult to squeeze them onto this one slide. So I think some kind of redesign is due very soon to show how many excellent members we have. And they are highly diverse, as indeed are nanomaterials themselves. So we have members that work within commercial production and use of nanomaterials. We have professional services and product development, which are a vital part of being able to deliver nanomaterials through to a market scenario. And we have amazing research centres and universities that really are producing the next generation of nanomaterials, that are looking at the next generation of safety of use of those nanomaterials, and working as an interface with industry to ensure their successful crossover into our everyday lives. So from our regulatory perspective, we work in a fairly typical way in that we work across all regulatory frameworks, we work across all sectors, because as I've already said, nano is emerging in an increasing number of regulatory frameworks, and it's very important that those frameworks are fit for purpose, and also that companies know the pathway that they must follow to market. So we have a number of different activities that enables our members to be fully up to date and to work with policymakers and regulatory bodies around the world. We also work increasingly in policy support, as long-term regulatory frameworks will be guided by policy changes, and it's very important that these follow an evidence-based, realistic route. So, for example, this year we'll be looking very closely at the development of the terminology around advanced materials, which a lot of people will have heard in many places, but still yet lacks full definition and any sort of place within policy or regulation. We do know that it will play a major role in the next framework programme, Horizon Europe. So it's incredibly important for nanomaterials in particular that it is well defined and has a clear framework in which nanomaterials companies can work. From our business and scientific networking perspective, we're always super busy, and this webinar this afternoon is an example of that. We run regular webinars on nano in action and nano in business, looking at the different interesting technology applications, but also the business frameworks around that. We have our annual symposium, which has been bumped to October, obviously with our current scenario. It was not taking place in March. We do a lot of work online, so we're building our LinkedIn community very strongly to make sure that both our members and our messages can reach really far and we can engage people from all around the world. We work across all sectors, particularly through the Industry for Europe Coalition, which has over 150 different industry associations in Brussels working together for stronger industrial policy. And we work to showcase our members as much as possible. So our Nano Pavilion, which you can see on your screen, was something we developed last year to enable our smaller members to be fully showcased at international trade shows that they would not otherwise be able to take part within. And finally, we take part in a number of EU-funded projects that really focus on the development framework for nanomaterials. So it looks at all aspects. So it looks at the innovation side of it. It plays a large role for safety in there, of course, increasing focus on regulation and standards as we become better able to manage and understand nanomaterials. And so these projects are all an integral part of helping build the wider economic ecosystem for nanomaterials. There's lots of different ways you can get involved. You can sign up to our newsletter, you can follow us on LinkedIn, and of course you could even consider becoming a member, of course, so that you could be part of these activities and help drive what we do to support the development of nanomaterials. But I will not say more about NIA, and I will get on with the show as that's what you came here to do. So I'm very pleased to give a short introduction to our first presenter, who will be Promethean Particles, and look a little bit at what drove the topic for this webinar. Because as in a lot of different sectors, this is nothing unique to nanomaterials, the scale up of an initial innovation is incredibly important. It is a significant commercial milestone, and you have to get it right if you're going to effectively get to market. You have to address all aspects of your product once it reaches the market through manufacture. So that will be how much it costs to manufacture, how safe is it to manufacture for the people exposed to the material during its manufacture and during its storage and transport. Can you manufacture it reliably? Will you be able to say with confidence to your clients that you are going to be able to provide them with a long-term material with a highly standardized quality? And as we, again, with many sectors, the initial innovation stages do not represent a product on the market. It's the first 5% of the innovation of that product, and the rest of the journey is all about making sure it can reach the market at the right cost and in the right scale, so it's usable in final products. Nano has the added challenge in that its very size gives it unique properties, which is what you want, but it also adds the challenge of being able to scale up its production and integration into products. And so that is something that always has to be taken care of within the scale up of the manufacturing process. And nano, as a relatively young economic activity, it needs manufacturing itself to become more mainstream so that it's easier to translate novel particles and products into larger scale production and use and integration into products. And a lot of our members, where they're looking at early stage development, you're looking at small scale batch production, which is great for working with in the in the lab, but it's no good. That is not how you're going to produce large quantities of it on a reliable, regular basis. So it's really about how you create the regular and reliable creation of larger scale amounts of your material. And this is really what our two speakers are going to speak about today. I'm extremely pleased to have our first speaker as Promethean Particles, which is an SME based in the UK that, based on its own technology platform, has now become a successful scale-up manufacturer of materials, working with clients from all around the world in all different sectors. So they bring a very interesting perspective to how they see scale-up needs and how they address those needs. We will then move to the absolute opposite of the spectrum and go to a large international company, which is Corning, which is, as you can see, almost 170 years old and a truly worldwide company. And its contribution to nanomaterials manufacture is based on its long history in glass and ceramics. So that they've come into nanomaterials production from a very different perspective. So what I'm going to do now is hand over to Selina, who will be our first presenter. So you will have to bear with me around because I've got to find Selina out of our huge list of people that are taking part today. And she's S, so she's really far down the list. But Selina, perhaps you could introduce yourself and, oh, Sean's already done it. That's great.
She's already done.
That's lovely. Thank you very much, Sean. You are much faster than me. So I will put myself on mute and Selina can introduce herself. And thank you very much, Selina, for taking part today.
Brill, thank you so much, Claire. Yeah, thanks for this opportunity. And hopefully I'll deliver an interesting talk for everyone today. So yes, my name is Selina Ambrose and I'm the technical manager at Promethean Particles. So today I'm going to provide a bit of an introduction to who we are and what we do, and importantly, talk about our manufacturing technology and the scales of operation at Promethean. Then I'll briefly cover some of the drivers for scale up, so why our customers come to us for scale up of manufacture. Then I'll talk a little bit about our internal methodology at Promethean when we're addressing scale up, and some of the technical commercial considerations that we have to bear in mind during that process. And then I'll wrap things up with just a summary of some of the benefits of scaling up with a continuous flow process, which is the approach we take at Promethean. So perhaps some of you are already aware of Promethean Particles, but for those who haven't come across us before, we're an SME based in Nottingham in the UK, but we operate globally. So we have customers from Japan and North America, as well as all over Europe as well. So as Claire said, we offer contract manufacturing to our customers by developing a scalable process for producing nanomaterials. But as well as that, we develop our own nanomaterial products and then participate in collaborative R&D projects as well. So they may be national projects funded by Innovate UK or European projects, for example, under the Horizon 2020 framework. So we've got a few of those active projects at the moment. So I won't go into too much detail about our technology today, but there's a nice video on our Promethean website which shows an animation of our process, or if you want to contact me afterwards and to find out more, then please do so. But in a nutshell, we use a wet chemical process. We're using hydrothermal or solvent thermal synthesis to produce our nanomaterials, but most importantly, it's a continuous flow process, not a batch process. So we see several benefits for our technology. Because it's a wet chemical technique, so what's happening there is we have our liquid raw materials pumped into our reactor systems. We then heat the liquid precursors under pressure, and that leads to particle nucleation. We're operating at temperatures up to 400 degrees Celsius and pressures up to 240 bar. But this is all done in a safe manner because we're using thick-walled stainless steel to manage everything. So after we produce our particles, the product dispersion product stream is cooled and depressurized, and our liquid product is collected at the end. And we have control over all the process parameters, such as the temperature, the system pressure, the types of raw materials, and the concentrations we're using, as well as the solvents or the flow rates. So there's a high degree of versatility and flexibility within the process. But because it's a wet chemical process, there are several benefits, from health and safety benefits, that we're not handling dry powders, particularly pertinent when it comes to nanomaterials. But also from a technical point of view, using a solvent-based technique can have its benefits in terms of reducing agglomeration or protecting the particles against oxidation from the environment and that sort of thing. And then because it's a continuous flow process, scale up is arguably simpler than scaling up a batch technique. Then from a cost point of view as well, the operating costs are relatively low compared to batch techniques. So at Promethean, we have bench scale reactors that we use mainly for rapid prototyping rather than production. So these are producing dry weight equivalent of a couple of grams per hour. So these systems are used to optimize the product for R&D purposes. And then once we've optimized that synthesis process to get the material that we want, we can then scale it up to one of our pilot scale systems. So these have the capacity to produce anywhere from 1 to 10 tons per year, dry weight equivalent. And so these are used for production as well as proof of or to demonstrate scale up from bench scale. So in the design of these reactor systems, there was a lot of modeling and CFD, computational fluid dynamics studies that went into studying the fluid mixing within the system to make sure that the pipe diameters we were using were scaled up appropriately to maintain that homogeneous turbulent mixing in the system. But like the bench scale systems, these pilot scale rigs still are fairly flexible in that we can use a range of operating temperatures, a range of pressures and flow rates. So it's we can use quite a few different processes and make a few different materials on these rigs. To date, we've probably upscaled about 50 different processes from bench to pilot, and we've seen very good reproducibility in terms of particle characteristics. So we're confident that any process we develop at the bench scale can be upscaled to pilot. And at pilot scale, that's sufficient to meet production demands for some markets, but in others, 10 tons per year isn't sufficient. So for that, we were very fortunate to be part of the European project where we got to design and build this system here, which we're very proud of. We call it our Infinity series, and it's the largest reactor system of its kind in the world. So as part of the European project that we worked on called Scheiman, we collaborated with chemists, chemical and process engineers all across Europe to design and build this system. So again, there was a lot of modeling and CFD work that went into looking at the fluid mixing within the system and keeping it consistent with upscaling. In addition, with the Infinity series, heat recovery was built into the process to increase the efficiency of the process and also ensuring that that sustainability aspect is maintained. Even at this scale, there's some degree of flexibility in that we can again control the operating temperatures and pressures, so we can produce a lot of different materials using this system. And to date, we've upscaled probably around 7 different processes onto the Infinity series, and again, we've seen very good reproducibility even at this scale. So we operate it on a campaign basis, producing one material, and then we have a clean down procedure, and then once that's in place, we produce another material. And the beauty with it being a continuous flow process is that if we need to produce a larger volume of a certain material, we can just run it for longer. So then when it comes to drivers for scale up, or why companies come to us for contract manufacturing, there's no one answer, and we found that it very much depends depending on the type of customer. So it could depend on the size of organization or the target market, or just their commercial interests, really, as to why they seek an external source for scale up. For some companies, they may have synthesized a small volume of a nanomaterial to then go into a device or another application, and their interest is actually in the device, and the synthesis of the nanomaterial was just a proof of concept. So as they scale up, they're not interested so much in the nanomaterial itself, but in the device manufacturer. So they want to outsource the nanomaterial production, and that's where we can come in. In some other cases, the customer may currently have a batch process, but because they see an increase in demand for a material, there are limitations to how much they can scale up with that batch process. And to produce more, it may mean they have to put in additional capital to buy additional equipment, and that may not be something that they can do. And it may be more cost effective or more innovative to just come to Promethean with that instead, rather than trying to do that all of themselves. And then in some other cases, it comes down to health and safety, actually. So some of our customers may have developed a process or developed a material using a process that can be exothermic or leads to a pressure buildup. And that can be particularly dangerous, especially if they're using a batch vessel, where the pressure buildup essentially means that they're handling an explosive device. So then that's just not feasible to scale up. So then they're seeking a continuous flow route instead, and that's where our technology can really provide some added value there. So as I mentioned, as well as conducting feasibility studies and scale-up projects for our customers, we have our own product development at Promethean. So I'll talk about a little bit about that there. So the images here just show some of the products that we've developed and now sell on our web store. So we've got copper on the left. In the middle is a metal organic framework structure, which I'll talk more about metal organic frameworks a little bit later on. And then on the right there is an iron oxide. So as we're thinking about new products and developing them, even at the conceptual stage, we have to think about the bigger picture questions. So thinking about the market demand, because as cool as blue sky research can be, as a business, we ultimately have to address a market demand, and our products have to meet a need. So it's identifying that need. And then we also think about our technology. What's the USP? Is it offering something different to what's already on the market? Can we make it cheaper than what's already out there? Can we make a better product? Or is it simply that the demand or the supply currently available just doesn't meet the demand? So those are the drivers for why we develop our own products and go down the upscaling route, because there are plenty of suppliers out there making titanium dioxide for pigments, so there's no point us trying to reinvent the wheel, so to speak. Then we also, from the conceptual stage, think about any obvious barriers to scale up. So with some materials, there are very niche, specific raw precursors that are needed to make that product. And it may be difficult to source and may be difficult to, or expensive to buy in. And that can be a real barrier to upscaling. And then also if there's any specific equipment that we don't have that's needed for making that material, processing it or purifying it, then that's something we need to consider even from the early stages. But ultimately, if we identify a strong need and we know that we can offer something different to what's on the market there and disrupt the market, then we ask ourselves, how can we overcome these barriers? And that's part of the innovative streak of within Promethean. So with the products that we've prototyped at the lab scale, and then we're thinking about upscaling to the pilot scale, there are several technical and commercial considerations that we have to factor in. And I've put the technical and commercial considerations together because often they go hand in hand, even sometimes if you don't realize it. But the important thing is that all these factors need to be reviewed regularly during the upscaling process because things can change both internally and externally. So for us, when we've prototyped at the lab scale, we need to define a specification. So what are the key material characteristics that will be a marker for success? It's not always particle size. It may be a bit of a red herring there, and it may be that your purity or your size distribution is the key thing there. So it's understanding what the goalposts or where the goalposts are and what the target is, because ultimately when you've upscaled the material, yes, certain parameters can change, but are the key parameters still the same? Because that's how we can identify success. And then that will feed into the quality control procedure for that material, not just the QC for the end product, but also QC for incoming raw materials and inline QC as we're producing the material in a continuous manner. Then health and safety is always something that needs to be considered, because at the small scale, handling a hazardous chemical may not be too bad when you've got just a few milliliters or a few milligrams of it. But then when you're scaling up to 100 liters or several kilograms of handling this chemical, then you need to think about any extra measures, so extraction or any extra PPE, and also safe storage of your raw materials. And then the product yield is something that is important to try and maintain with scaling up, or if you can increase it further as you scale up to make the economic viability better. Shelf life is something that's important as well, because we need to think about whether we can make the material ahead of time and then store it in the warehouse, or if it needs to be made to order, because that's going to affect the commercial viability or some of the costings as well. regulations is a very important one, and if you're a technical person, something that can often be overlooked. So things like licenses for raw materials, now that's going to differ depending on the country you're operating in, and then things like registering your products, so it may be a chemical specific registration or volume dependent. And then there's also things like transport. For us, because we're contract manufacturing materials for our customers, after production, we need to think about shipping. So if it's a hazardous goods, then there are certain regulatory things we need to think about, like packaging and also all the paperwork that the couriers need. And then, of course, money comes into it. So we need to think about the cost analysis and the scale of operation. Because we're using a continuous flow process, economies of scale plays a very, very important role. Essentially, the more we make, the cheaper it is per unit. So per kilogram of material decreases with the increasing scale. So we need to identify this scale of operation where it becomes cost viable, and also how that balances with demand. So I've got a couple of slides here with an example of one of the products we've developed in the lab and then upscaled, so the metal organic frameworks. So MOFs are a group of compounds that are highly porous and have a very high specific surface area. So they're useful for hydrogen storage, carbon capture, as well as catalysis and those sorts of applications, chemical separation as well. So this material here is called ZIF8, and we identified a demand and a unique selling point where our technology could offer something that wasn't available on the market, in that we could actually reach greater scales of production than currently being offered. So we prototyped the process at the lab, developed a procedure for manufacturing this material at a small scale, and we got the crystal structure that we needed and the surface area that was in line with what was reported in the literature. So then we started looking at scaling this up to pilot scale. So at this level, we were producing about up to about 1 kilogram per hour dry weight equivalent. And with this material, the crystal structure and the surface area are the two key characteristics. So that starts to form our spec. As we produced it on the pilot system, the crystal structure was spot on, the surface area was in the right ballpark, but the particle size and the morphology was slightly different. So this is what I mean about understanding your spec, because different isn't necessarily bad. It's, in this case, it doesn't affect the end performance because the surface area is still what it needs to be in the range. So in this case, we can consider this scale-up process a success. More importantly, well, as importantly, the economics of the system is sufficient in that the costs of producing at this scale is enough that we can offer this product on the market for sale at 1/10 of the price to other suppliers currently in the market. So there's this balance between the technical priorities and commercial priorities there. And then even with getting this product on the market and achieving scale up, we're still looking at improving the product more. So since this publication, we've been able to increase the BET surface area up to 2,000 meters squared per gram, and also increasing the yield to make it even more cost effective. So finally, to summarize and conclude, with using a continuous flow process to address scale up can have several benefits. So because we're take a just-in-time manufacturing approach, we're producing material and we can have a QC protocol as the material is coming out of the system. So we can very quickly identify if something is not quite right, and then rectify it, which means that we're minimizing the amount of waste. We're not having to discard an entire 1,000-litre batch because something's gone wrong. We can react quite quickly, and that means that the process is an efficient and sustainable one. And because we can control our process parameters, we can fine-tune conditions and optimize at scale. We're not having to go back to the bench scale and re-optimize and then scale up. We can do it at the pilot scale as we go along. And then the multi-material flexibility means that we can scale up lots of materials using the same equipment, which means that we're minimizing the capital expenditure. We're not having to have separate reactor systems for each material. And then from a health and safety point of view, compared to batch systems, our continuous flow reactor systems aren't closed vessels. We continually have raw materials coming in, product going out, so it's easier to maintain pressure, so not having unexpected pressure buildup or any exothermic reactions, so regulation is a lot easier of the process. And finally, because of the economies of scale, scaling a continuous flow process means that the operating costs or the cost per unit comes right down with increasing scale. So at that point, I'll wrap up. And
thank you very much indeed, Selena. I think I've just accidentally muted you, so I'm very sorry about that. That was a really great presentation. Thank you very much indeed. And it's very interesting to see when you said that you're often the scale-up particle may actually be slightly different than the original particles developed. And of course, when you look at REACH dossiers, that's a very important factor to take into consideration. So you have to ask your question as to what your dossier is going to contain to ECHA, whether it's the original material you've produced or the scaled up version of that same material. So I am now going to hand over to our next speaker, Philippe Roth of Corning, and Sean is very kindly doing that job for me. So I hope that I see the handover is fine there. Philippe, do you want to say hi? Because I thought you were caller 2 and caller 2 has now left. So hopefully that wasn't you.
Oh, hello.
Oh, there you are. That's lovely. Thank you very much.
All right. Yeah, fantastic. So, yeah, thank you. It's my pleasure to be here today. Thank you very much for your kind introduction. So, as you can see, I'm an application engineer working at Corning. And it is my pleasure today to welcome all of you here to deliver my quick presentation on the Corning Advanced Flow Reactor as part of the NanoIn Business Group. My role is to be the technical support for the customers. Let me guide you quickly through our agenda. After a few words regarding Corning in itself and presenting the IFR business, I will show you an example using the equipment and displaying excellent reproducibility on bimetallic nanoparticles. Then I will discuss of another example of quantum dot synthesis, showing scalability, and finish with another application on photochemistry before concluding. All right. So, Corning is an old and well-established world-leading company specialized in glass and ceramics. Its core philosophy is based on innovation and research to change and improve the life of people. It is a global company present worldwide, striving to bring technology everywhere. Corning is used to produce mass market products which improve the people's lives. The core innovation has been present throughout Corning history and is more true now than ever. Corning has been upscaling everything during its whole life. Among the things Corning has developed for the market, one can notice the Pyrex glass, television picture tube, optical fiber, and the Corning Gorilla Glass, which equips millions of mobile phones worldwide.
Hey, Philippe, are you having a few problems with the slide changes?
Yeah, well, I mean, yeah, it's kind of slow for you guys.
Well.
Amongst the, yeah, that's good. I'll carry on. Among the glass innovation, AFR is a Corning business which uses an integrated glass design to perform flow chemistry. In this device, reagents go through the plates, which we call fluidic module, in which a controlled chemical reaction can occur smoothly. This unique technology combines a sandwich structure in which the reactive pathway is stuck in between two heat exchange layers, making sure the heat transfer is excellent. As can be seen now, the three layers can be seen, and although very, very close, and the specifications are pretty large for our reactors. The slide shown here describes the specificity of the AFR reactors. Firstly, the reactive pathway incorporates a number of heart-shaped exchangers in row, which ensures top quality mixing throughout the reaction pathway. This is especially true in the case of non-miscible phases, such as liquid-liquid or liquid gases. Then, as shown in the previous slide, the heat exchange surface is very high and ensures an excellent heat exchange property for our reactor. Making most of the experience from Corning, our reactors are highly chemically compatible, as we are either glass options or top-grade silicon carbide material to make them. This ensures a total chemical compatibility for all types of chemistry in application. Another key property is that all the AFR reactors have been designed to seamlessly scale up. This unique property was engineered from the start to ensure a consistent mass transfer as well as a heat exchange coefficient across all of the AFR portfolio. This means a reactor will behave the same at any scale. This property is an excellent feature, helping customers to go from a lab to the production scale. And last but not least, Corning has acquired experience over the years in selecting the best devices around the reactor, and our engineering team can design custom-made solutions and offer turnkey features to our customers. So, let me introduce you to the Corning AFR portfolio. It covers a wide range of metal-free and highly modular reactors from laboratory to industrial scale. This includes the lab reactor, which has been designed for the people starting in flow chemistry, and the photochemical version in the lab photoreactor. We are adding as well the low flow reactor, which is more modular, and all these products deliver flow chemistry at a range of few milliliters per minute. When one scales up, Corning offers the G1 reactor at the pilot plant scale, which exists in different versions, from the glass on the top to silicon carbide, and with the possibility of photochemical option by adding an optional LED panel module. Upon reaching the scale up at the industrial scale, there is a G3 which can process up to 1,000 tons of product. It is also available as a photochemical reactor. Last but not least, Corning's largest reactor to date is the G4, which is made of silicon carbide and can deliver throughput in the range of a few thousand tons of processed product per year. Of course, today we are going to discuss application of nanoparticle synthesis within the reactor I've shown previously. The first example will focus on reproducibility. AFR collaborates with external companies. One of these external research institutes investigated the repeatability of processes. This institute started a project aiming at speeding the process of going from the laboratory up to the real industrial production scale. More specifically, as a benchmark product, they selected a fuel cell catalysis synthesized with two metals. The aim was to test the synthesis. They decided to test it on our equipment, as you can see on the picture down below, with the dosing line module and the reactor. Slow transition. Yeah. So the synthesis was to be made from milligram scale to up to kilogram scale. The initial work that the people have done was performed in batch. Unfortunately, the scale-up of the methods proved unsuccessful. It was highly user-dependent. Facing this issue, the researcher turned toward flow chemistry to address the challenge. Indeed, if the reaction worked out, scaling it up would be easily helped by the fact that the Corning reactor portfolio is especially designed for the scale-up. The nanoparticles synthesized here were made of platinum and nickel. The first good news is the process could be transferred smoothly from batch to flow chemistry. The first aspect people wanted to check was the quality of the product over time, and they did it. The scientists performed the synthesis over an extended period of time and collected samples to perform in more depth analysis. As you can see here on these pictures from the analysis, nanoparticle shape and size obtained in batch and flow was very similar. Interestingly as well, one can notice that the results are essentially identical even after hours of continuous production. This is indeed the case as the reactor has reached its steady state level and will deliver a reliable product as long as it is fed with starting material. After the synthesis, the best way to actually test the nanoparticle is to use them. The nanoparticle catalytical activity was evaluated and tested as fuel cell catalyst. For the test, commercially available nanoparticle was set as a reference. As can be seen in the illustration below, the catalytical activity of the nanoparticle produced in flow, which are in red, is slightly higher than the one produced in batch. Additionally, they reach higher uniformity when compared to batch. Further specific analysis revealed that the nanoparticles were indeed incorporated both platinum, which is in red here, and nickel, which is in blue. This even distribution finishes to demonstrate the effectiveness of the process. So this concludes the first topic of work performed by this external research institute. So now I will talk about the quantum dot synthesis. So this work was actually performed by Professor Jean-Christophe Montbalieu in Liège University in Belgium. He and his team decided to work with a low-flow reactor. They worked with a synthesis involving cadmium salt reagent and performed the reaction in water. This is known that this solvent can be challenging for this type of synthesis. So they modified an existing procedure to adapt it to make sure it would perform well using flow chemistry. The results can be seen below. Essentially, by controlling the residence time, one can control the size of the quantum dots. This can be seen as well by the picture of the vials. The strong correlation shows the easiness to control the quantum dot size. Indeed, the residence time can be modified pretty easily by adding or removing fluidic module on the reactor. This on-demand production is a new way to easily control the synthesis and make most of the equipment to deliver high-value products. So to summarize here, quantum dots were synthesized in ecological friendly solvents in a reliable way by controlling the pressure to produce on-demand quantum dots in a laboratory scale. Moving on from there, the work was repeated in a G1 silicon carbide reactor. The transposition worked out well. Using the higher scale, work was performed to look into the pH effect. So as previously mentioned, when one increases the residence time, the size of the nanoparticle increases. But using this setup, they could see as well that increasing the pH increases the size of the quantum dots. This was possible because of the strong chemically compatible nature of the silicon carbide used. So this example shows you that it is possible to finally make quantum dots using flow reactors. So far, we've seen nanoparticles made of platinum, nickel, and cadmium, but there is more than that. So let me introduce you to nanoparticles made of the most precious metal. I am, of course, referring to gold. In this case, the nanoparticles are synthesized in flow with photochemistry. This is an aspect I've briefly mentioned earlier. A very common way to synthesize gold nanoparticle is to use the Turkvetich method using citrate and a photosensitizer. Here is the equation, and the photosensitizer, there are different tips. The reaction tends to work well, but there are important drawbacks in terms of repeatability, and scalability is very complicated. Here it's a series of photosensitizer. So in this case, the people decided to work in flow chemistry. Optimization work of the reaction was performed in the lab photoreactor. And the following scheme here shows you the setup of the system. So essentially there were 3 inlets, one with the aqueous phase of photosensitizer, one with gold, and one with the stabilizer. All these chemicals were premixed and injected in the reactor where the mixture underwent photoillumination. Based on this design, a very fast screening of condition can occur. When it comes to the result, the good news is that it works very well. Here again, longer residence times mean larger nanoparticles. Here, as well, UV spectra on the right-hand side on the picture display good quality of product. And while performing this work, a lot of interesting knowledge was acquired. On the bottom here, one can see the postulated mechanism. So different things actually were met, different type of issues. And one of them was actually the fact that nanoparticles, gold nanoparticles, tended to form a gold mirror, as can be seen on the picture. And this prevented light to go through the reactor. This possibly as well impacted the real residence time. Attempts to coat internally the surface of the glass proved useless. Addition of stabilizer as well was performed to improve the situation, but it only improved the nanoparticle stability once they were formed. So last but not least, varying the condition helped to avoid the issue. This way was successful while maintaining good property of the product. After the reaction was made, at laboratory scale, trials in pilot plan was done in the G1 photoreactor to validate the scalability, and after this quick test, actual testing on the G3 photoreactor was carried out to prove the scalability in a real industrial level. This work has just been published. You can see underneath the link to the paper. I would encourage people to have a look at the scale-up strategy where everything is displayed in more detail. So I would conclude here and summarize that AFR technology is a market-disrupting tool which allows the production of highly controlled and repeatable nanomaterial products. Advanced flow reactor offers a wide range of products and reactor with a seamless scalability, which is the core property for all of our products. Once optimized at laboratory scale, a product can be moved to industrial scale in a very timely fashion. And last but not least, our product offers photochemistry in a controlled way at all scales if required. So I would like to thank our collaborators, which allowed us to be named. So the University of Liège. I would like to thank all the people who attend this webinar, and the NIA who invited us to give the talk. Of course, if people have questions, there will be a Q&A answer for the NIA members. But for the other people who want to get in touch, feel free to do so. You can see on the screen my contact details, so feel free to send me an email or send an email to my colleagues, or just contact me over the phone. So, and that's it now. I will hand over the control back to the main presenter, but thank you very much for this opportunity.
Thanks very much indeed, Philippe. That was really interesting. And as with aspects of the Promethean presentation, it's amazing that the properties of materials at the nanoscale themselves are a challenge when you come to things such as manufacturing, because they're so highly reactive and highly changeable. It's a fascinating thing to look at. So I would like to thank everybody very much for being part of the webinar today. We are going to take a short break for 5 minutes now so that we can get the closed session active. So I would invite all the Corning employees and NEA people, NEA members to stay within the webinar, and everybody else can go and get themselves a well-earned cup of tea or coffee. And we will contact all registered delegates with the recording of this webinar as soon as it is ready, plus some of the slides from the meeting. We welcome any queries that you have. You can contact both of the presenters directly, and we hope that this was an interesting insight into how nanomaterials look at the scale-up process, as it's a fascinating aspect of nanomaterials development in its own right, even after you have come past the point of innovation and developing a novel particle. So thank you very much indeed, everybody, and we hope to see you in future webinars that we host. And it's always very interesting to hear from you. So I'll put everybody on mute now, and we look forward to talking with our members in 5 minutes' time. Thank you very much.